For global normalization, C sub jk is assumed to be the same for all spots j on array k. An underlying assumption is that the red and green intensities are related by a constant factor, r equals k times g. That is, there is a linear relationship between the red and green intensities, and that the linear relationship goes through the origin. Also, global normalization assumes that all cDNA species within a sample will incorporate at an equivalent amount of dye per mole of cDNA, and there are no other variables that contribute to dye bias across the slides. Therefore, to perform global normalization, a constant function equal to the mean or median of the log ratios of signal intensities may be subtracted from all spots. A related method is to fit a linear regression with a zero-intercept and use the estimated slope parameter as the constant. Thus, global normalization applies a linear transformation to the data, which shifts the distribution up or down without changing the shape of the distribution. A variant of this approach assumes invariance for a subset of genes, typically housekeeping genes or genes empirically determined to be invariant, and uses only those genes in the invariant set for estimating the constant normalization factor. Because regression can be used in global normalization and is frequently used in intensity-dependent normalization, let's review linear regression. Regression considers the frequency distribution of one variable when another is held fixed at each of several levels. Alternatively, correlation considers the association between two random variables. Given we have a set of data, how can we estimate the regression line? Our goal is to find the line that minimizes the vertical distances to the data points. In fitting a line to the data, we postulate that there is a probability distribution of y for each level of x, and the means of the probability distribution vary in some systematic fashion with x. Typically, we do not know the values of the slope and intercept for the best line, but we need to estimate them using the data. Suppose we have 2 points and that we plot them on a Cartesian coordinate system, and a straight line is drawn connecting these 2 points. Recall that the equation of a straight line can be written in point-slope form using this equation, where m represents the slope of the line and x1 and y1 is a point on the line. The slope of the line is given by rise over run, which is given by this equation. In our example, we have this result. Usually, the equation of a straight line is written in slope-intercept form, or y equals mx plus b. Of course, we can rearrange this so that the intercept is first, or y equals b plus mx. Reducing the point-slope form of the equation to slope-intercept form, we get this result. This equation describes a functional relationship between the variables x and y. In the real world, such a relationship may not be perfect, but rather a statistical relationship may exist. That is, we may have many pairs of observations to which we want to fit the best straight linear relationship. Regression considers the frequency distribution of one variable when another is held fixed at each of several levels. Our goal is to fit a line that permits some error, since the linear relationship is not perfect, and the model we will use is y equals beta naught plus beta 1 times x sub I plus e sub I, where y sub I is the response or dependent variable, beta naught is the intercept, beta 1 is the slope coefficient, x sub I is the independent predictor variable, and e sub I is the error, where the expected value of e sub I equals 0 and the variance of the error terms is sigma squared. Thus, the expected value of y sub I is given by this equation, which can be simplified by noting that the expectation of e sub I is 0. The method of least squares considers the deviation of y sub I from its expected value beta naught plus beta 1 times x sub I. To fit a line to these data such that the vertical distances from the fitted values to data points is minimized, we want to minimize this equation. To find the values of beta naught, the intercept, and beta 1, the slope, that minimize the equation Q on the previous slide, we want to take the derivative of this equation with respect to beta naught and then take the derivative of this equation with respect to beta 1. Then we have two equations and two unknowns. We then set both equations equal to 0 and solve simultaneously. The solution to the best fit problem is then this equation for beta 1 and this equation for beta naught. Of course, we won't be using these formulas in this course, but rather we will use R to fit a linear regression model for us. The function for fitting a linear model is LM, and the response is modeled by the predictor variable, which, if these are stored in a data frame, the name of the data frame is passed to the data argument. Most often, we want to use the fitted models to perform various other tasks, so we put the fitted linear model into an object using the assignment statement. For example, we could then use the summary function on our fitted modeled object and get information about the fitted regression model. The fitted values from the sample data are obtained by substituting the x values in the sample into the estimated regression function. The R function predict returns the fitted values. Again, the function for fitting a linear model is LM, and the response is modeled by the predictor variables, which, if these are stored in a data frame, the name of the data frame is passed to the data argument. You can print the fitted model to the R console by simply typing the name of the object. The resulting object fit is of class LM, which is a list, and its components can be further operated on by additional functions. For example, if you type names fit, you will see different components that can be extracted. We can test the null hypothesis, H naught, that the slope estimate beta 1 is equal to 0 against the alternative hypothesis that the slope beta 1 does not equal 0, using the output from summary fit. Note the slope is estimated to be 3.82 and its standard error is 0.1634. Dividing the estimate by its standard error yields the test statistic, which is 23.37. This statistic follows a t-distribution with n-2 degrees of freedom, where n is the sample size, and 2 degrees of freedom are lost from estimating the two parameters, the intercept and slope. The p-value can be looked up using tables, though R provides the p-value in the output. Because the p-value is less than the standard 0.05 level, we reject the null hypothesis and conclude that beta 1 is not equal to 0. The linear regression model includes 4 different assumptions which can be remembered using the mnemonic line. This includes linearity, or that the expected value of y given x is a linear function of x. Independence. The error terms are independent of each other. Independence is assessed by carefully considering the study design. If subjects are recruited in clusters, for example, members of the same household, or if the same subjects contributed repeated measurements to the data set, then the independence assumption is violated. Normality of the errors. The error terms are normally distributed and equal or constant variance. That is, the variability of E, the error term, is the same for all values of x. This latter assumption is often called homoscedasticity. In other words, it assumes that the variance is the same for any level of x, or that the variance of y at each level of x is constant. In our example, we would have this assumption. Therefore, the fitted model should always be assessed to determine whether these assumptions were met. This can be done by examining the residuals, which, because our regression model is given by this equation, where E sub I are the true unknown unobservable errors, the observed residuals E hat sub I is equal to Y sub I minus Y hat sub I are our best estimate of these errors. So residuals are simply the difference between the observed value of Y and the fitted or predicted value of Y. We can examine plots using the residuals, often called diagnostic plots, to check these model assumptions. This includes examining a scatter plot of residuals versus fitted values, a scatter plot of fitted values versus the observed data, a normal quantile plot of the residuals, and a plot of Cook's distance. Passing the fitted object to the plot function in R produces these four plots as seen on the left. This includes a scatter plot of residuals versus fitted values, which can be used to assess linearity and equivariance. When examining this plot for linearity, we don't want to see any pattern in the plot. If there is any curvature or nonlinear pattern in this residual plot, that would indicate that linearity is violated. When examining this plot for equivariance, we would want to see random scatter about the line E hat equals 0, such that there is equal spread up and down all along the plot. If we see a fan-shaped pattern in this residual plot, that would indicate the equal or constant variance assumption is violated. The normal quantile plot of the residuals is used to check whether the model meets the assumption that the errors are normally distributed. This is a plot of the observed residuals against the theoretical quantiles of the normal distribution. If the residuals are approximately normally distributed, the points on this plot should be a straight line. We should also check for outliers on the residual plot, as outliers may have undue influence on the fitted regression model. However, we should never just throw out data points because they are outliers. Only remove a data point if it is confirmed to be a mistake, for example, a data entry error. Plots of the square root of the standardized residuals versus the fitted values and Cook's distance can be used to identify outliers. We may also want to examine a plot of our observed outcome Y plotted against the predicted outcome to see if the fitted linear model looks reasonable. Sometimes the regression line is known to go through the origin at 0, 0. For example, global normalization for custom spotted arrays assumes there is a linear relationship between the red and green intensities and that the linear relationship goes through the origin. The normal error model for these cases is the same regression model, except now beta naught is equal to 0. Thus, the regression model is given by this equation where beta 1 is the slope parameter, x sub I are the known constants, and E sub I are the independent error terms assumed to follow a normal distribution that has a mean of 0 and a variance of sigma squared. Another way to write the regression model when beta naught is not included is that the expected value of y equals beta 1 times x. Again, the least squares estimate of beta 1 is obtained by minimizing the objective function for this model with respect to beta 1 by taking the derivative with respect to beta 1 and setting the expression equal to 0. To fit a line with no intercept, you simply write the model syntax in R as before, but subtract 1 from the right-hand side of the model formula. That designates that the intercept estimate should be coerced to be 0. Recall that for a custom spotted array, there are two channels. Ordinarily, we call them red and green, but to put them in the context of a linear regression model, we will call them x and y. After fitting a linear regression model without an intercept, the intensities for the normalized array would be either given by this first equation or by this second equation. So only one channel's intensities are modified. Therefore, this global scaling method essentially simply shifts the distribution up or down without changing the shape of the distribution. There are some disadvantages of global normalization. First, it does not account for the nonlinearity of signal intensities. And second, it assumes cDNA from both floors or dies have equally hybridized across the array. Therefore, intensity-dependent normalization methods are more commonly applied.